Okay, we have another pretty interesting example here that is going to introduce us to a concept we actually saw in the craps example from before, but it's another powerful technique, very powerful technique called recursion. And recursion really depends on this idea of independence for us to be able to use it. Okay, so it's just an example, so it's not a general general situation. Let's assume we have a game. So suppose we have two players in a game. Let's call them A and B. And what happens is, to start, A puts up $2. B puts up $1. Based on the rolls of a fair die, so we're going to roll one six-sided die, A and B are going to trade money back and forth. So based on the rolls of a fair six-sided die, A and B trade money back and forth. Until one of them has all three bills. Okay. All right. So how do we do it? The rule is that if the die shows a 1 or a 2, A gets $1 from B. Otherwise, B gets $1 from A. What's the probability that A wins? Okay. What's the probability that A wins in this example? How are we going to do this? We want to set up a recursion. What does that mean? Well, it's really our only hope here is the probability that A wins. A can win in a couple ways, right? A can either win on the first roll, or if A doesn't win on the first roll, then the game continues. And the probability, what we have to remember is that the starting state, what's probably that A wins the game, given that A has $2 in his pocket, right? If at some future point in the game, in the 100th roll of this game, A gets back to having $2 and B has $1, by the independence of the toss of the rolls of this die, the probability that A wins moving forward is the same as it was to start, right? Because the game conditions have started over, right? Nothing that happens in the past is going to affect what happens in the future at that point. So what we can do is we can condition on the first, really we have to condition on the first roll. And this is a common technique, is we condition on some piece of the action. In this case, we can really only condition on the first roll. Sometimes when there's a start and a finish, a definite start and finish, we can also condition on the last piece, and that's also good to do. But right now we're just going to condition on the first roll. And let's write this as, let's just write this as P sub A. But implicitly, it's that A has $2. So probably that A wins given $2 is probably that A wins on the first roll. Given $2 and wins next roll. Probability wins next roll. Plus probably that A wins given $2 and loses the next roll. Probably of losing the next roll. All right, a lot of words here, but hopefully you get the idea. So what's probably that A wins given that starts with $2 and wins the next roll? Well, if we win the next roll, B is going to give $1. We're going to be up to $3. We're going to win probably 1. What's probably of winning the next roll? Well, it's tossing a 1 or a 2. So that's 2 out of 6, right? 1/3. And then what's the probability that A wins given $2 and lose the next? I don't know what that is yet. But what's probably of losing the next roll? Well, that's 4/6, right? So now I have to figure out how to get out of this, because once I'm in this situation, if this happens, I actually only has $1 left. And that's not the same condition as so this is actually the probability that A wins given having $1, and that's not the same. So I don't have what I want just yet. I want this probability here, this unknown quantity here, to match up with this quantity here. And then I'll have one equation, one unknown. So I have to condition again on the next flip, on the next toss. Because now it's, what's the probability? This is 2/6 plus 4/6 times probability that A wins given $1 and winning the next. Probability of winning the next. So we're just using law of total probability again. Condition on the first and condition on the next step. Plus probability that A wins given $1, losing the next, and probability of losing the next. Well, all right, now we're in business because we have what's probably that A wins given that they now have $1 and win the next. Well, that means they're going to have $2. So that's actually the probability that A wins given $2. What's probably of winning the next roll? Well, it's always 2/6. And then what's probably that A wins given $1, having $1 now and losing the next roll? Well, if you lose the next roll, you're giving $1 away. You're now down to $0. You lose the game. So that's probably 0. Okay, so now what we have is probably that A wins on the left-hand side. That's all the way up here. And we have this here. So equals 2/6, which I'll write as 1/3 now, plus 2/3 times 2/6. You know what? I'm going to leave these the same. It's not, it's just easier to make sure we're keeping track of everything. Times 2/6 times P sub A. So we can do a little algebra, and what we will conclude is that the probability that A wins in this game is 3/7. So A started with more money and has a 3/7 chance of winning this game, meaning B has a 4/7 chance. So B's in a better place in this game. Even though B starts farther away from the target, B has an advantage on each roll of winning 4/6 of the time, 2/3 of the time instead of 1/3 of the time. If both players have have three numbers instead of have three favorable numbers each, so they each have a 1/2 probability on each roll, so it evens out the game a little bit. Then the probability that A wins, we can figure this out. It's 1/2 plus 1/2 times 1/2 times the probability that A wins. So we would have to set up the recursion accordingly, but the numbers work out to be, we're going to get some similar calculations, just different numbers. But in this case, probably that A wins 2/3 at a time. So A wins twice as often, but A is also putting up twice as much money. So in some sense, that feels like a fair trade-off. This is a precursor to what's called the gambler's ruin problem. Gambler's ruin problem is a classical problem in probability involving coin tosses. Okay, here we assume dice rolls, but might as well be a coin toss because we're really just looking at binary outcomes on the outcome of a roll of die. Whether or not A gets $1 or whether or not B gets $1. And then the game ends when somebody runs out of money. That's the gambler's ruin problem. That's the problem that we're going to come up with and that we're going to talk about next.